Audible? Yeah, thank you. Good afternoon, ladies and gentlemen. It's my pleasure to welcome you to this session, which is Optimizing Efficiency and Risk Management in Refinery and Petrochemical Complex. As we all know today, that efficiency is no longer just about throughput or energy intensity. It's totally inseparable from sustainability, asset reliability, project execution disciplines, and overall risk resilience. Our refinery and petrochemical plants today are being asked to operate at higher severity, deliver low carbon intensity, and function with almost near zero tolerances for any disruptions of any type. So just to cover from these aspects, the 4 papers we have today, which will be presented and which will reflect this reality. Together, from end-to-end narrative across the life cycle of a refinery and a petrochemical complex, from a long-term strategy of decarbonization, project execution, design efficiencies, and equipment-level innovations, and finally, the real-time optimizations in a plant. So with these, I would like to welcome these opening words, our 4 distinguished speakers who will be presenting these various ideas to us today. First of all, I have Mr. Akshay Gupta. Mr. Gupta is a Senior Manager, Refinery and Petrochemicals and Renewable Fuels at Honeywell UOP. He leads the technology transfer activities and the team of process specialists and brings with him more than 25 years of industry experience. Next, we have Ms. Suhaini, and she is the principal structural engineer with over 22 years of experience in oil and gas and petrochemical industries. She is with McDermott, Kuala Lumpur, and she has a strong track record in delivering safe, robust, and cost-effective structural engineering solutions across offshore platforms, modular structures, subsea developments, and onshore processing facilities. Next, I have Mr. Indra Kumar Gore, who is with Kannan Engineering Industries Private Limited. He has over 14 years of experience in the field of heat exchangers, and he specializes in thermal and mechanical design of shell and tube, corrugated tube, plate and spiral heat exchangers, and he has contributed to the developing efficient and innovative heat exchanger solutions across diverse process industries. And finally, we have Ms. Rijumoni Boro. She is a chemical engineer with B.Tech and M.Tech from IIT Guwahati and over 9 years of experience in petroleum refining industry. She is currently working with IOC R&D Center Faridabad and is actively engaged in advanced research focused on upgrading low-value bottom-of-the-barrel products and optimizing the delayed coker operations across the refinery network. With our first speaker, Mr. Akshay Gupta, and his presentation will focus on developing a sustainable roadmap for optimizing and decarbonizing naphtha complexes, addressing low efficiency improvements, how efficiency improvements can be aligned with long-term carbon reduction and business competitiveness. Please give him a big hand.
Good afternoon, everyone. Thanks, IEW, for invitation. I would like to express my sincere appreciation for this opportunity to meet and speak with you today. Ladies and gentlemen, my name is Akshay Gupta. I'm the Senior Manager of Refining Petrochemical and Renewable Fuels at Honeywell UOP. Decarbonization is undeniably one of the most critical challenges of our time. Today, I'm excited to have the chance to tell you that how Honeywell UOP can help you in the energy transition journey of your naphtha complex. Here is the announcement that there may be some forward-looking statements in my presentation, so please be cautious on how you interpret or use such. Modernization of existing assets to reduce the CO2 emission is indeed a journey, and that looks different for everyone. It depends upon your goals, your asset, and of course, your budget. To help you visualize what a decarbonization journey may look like for you today, I would like to emphasize on 3 key areas. First one is the high-level overview of how CO2 emissions are distributed across the refinery and then a closer look on the naphtha complex. Secondly, I would like to emphasize on how we can assist you to achieve your goals, and finally, explore the solutions which has the greatest impact on your decarbonization journey. To set up the context, I have included a schematic flow diagram of naphtha complex here, where full range naphtha is being hydrotreated in naphtha hydrotreater and then slit for further processing. Light naphtha, which is C6 minus, is sent to isomerization unit for converting low octane naphtha to high octane naphtha. And UOP has family of offerings in this space. The Verizom and the Penex is common one. We have more than 350 licensees since late 50s for isomerization technology. Heavy naphtha is sent to platforming unit, where the value can be defined as the platformate for the gasoline pool or the feed to aromatic complex for BTX production. Again, UOP has variety of technology in this space. The CCR platforming and the fixed bed platforming is the quite common one. We have more than 375 licensees for the CCR platforming and more than 600 fixed bed platforming licensees since late 49. When we look at typical hydrocracking or delayed coker-based refinery, it is not surprising to see that the naphtha complex that we have just discussed is the third largest contributor of the scope 1 and scope 2 emissions. Therefore, this means that the optimizing and modernizing your naphtha complex to reduce CO2 emissions can be a great profitable and reduce the CO2 emissions from your facility. So what UOP Honeywell can, let us look at, from where these emissions are coming. So unsurprisingly, the separation followed by the fractionation, followed by the fired heaters and the compression. So this gives us an idea, the low-hanging fruits, which are the biggest needle mover in your decarbonization journey. So what Honeywell UOP can do for you? So we base our strategy in the 4 pillars. The first one is driven by the fuel to petrochemical pivot. So we have the slowing demands of transportation fuels and the growing demands for petrochemicals. Second one is the molecular management, which means that put the right molecules at the right place. What does that mean? That the molecules where it gives you the highest yield, consume lowest energy, and produces lowest waste. And the third one is the carbon capture, utilization, and storage, which is the first solution to turn when you want to reduce the CO2 emissions from your facility. And fourth one is, of course, technology and energy improvements. So opportunity exists throughout the platforming unit. What you can do from the starting reactor, you can replace the reactor internals to our CatMax proprietary internals to improve C5 and hydrogen yield. I have a detailed slide on this one. Maximizing the heater efficiency through convective heating or the tube coating, the feed optimization through the molecular management or the DW integration or the heat integration, maximize heat recovery through alpha level Pacinox or weighted surface air condenser. We also have chloride management solution, which is the RBG Chlorosorb from the chemical standpoint. And finally, the recovery max, where we maximize the LPG recovery and hydrogen recovery. We have a detailed slide on this one also. Also, similar to platforming, the opportunity exists in the Penex process to reduce the CO2 emissions for better utilization of reducing the energy intensity. So from feed optimization to molecular management to DWC integration, you can also deploy the MD trays or coated tubes, also column optimization through MD trays. We also have 2 chloride management solutions. The first one is the left-hand side is the Isomat, which improves your C5 yield and eliminates the anhydrous hydrochloride uses during the C2 regeneration. The second one is the right-hand side is the rechlor, which is the efficient chloride management to improve the chloride recovery and completely eliminating the caustic uses. So let us explore few of the solutions. The first solution I would like to talk about is the Recovery Max, which is the energy efficient and low cost recovery system to recover high value LPG, hydrogen and reformate from your platforming gases. This can be implemented as a standalone or as a revamp or as a modular UOP supply. Reactor effluent is routed through the separation section followed by recontacting, where the net vapor, which is the hydrogen rest, and net C3 liquid sent to Recovery Max. From Recovery Max, we recover high purity hydrogen and the liquid, which is the C3 enriched. Recovery Max increases the hydrogen supply and also reducing the demand for SMR hydrogen, also improving our refinery overall fuel refinery gas balance and enabling higher hydrogen and higher LPG recovery. Since Recovery Max enables higher hydrogen and LPG recovery, it also enables economic benefits. For a case study done on the 40,000 BPSD of platforming unit, we can see a significant NPV improvement of $36.7 million. And if you look at the emission reductions, 85 kmt of CO2 reduction, and if you take the credit of those CO2 reduction, the NPV, including the CO2 credit, is around 68.6 million. At Honeywell UOP, our focus is on 6 efficiencies. That is the E6 model. We are developing and directing the solutions which brings you the societal and environmental challenges. And these 6 efficiencies are carbon, that means put right molecules at the right place. Hydrogen, optimize the hydrogen usage. Utility, so from optimize the utility. CO2, strive for the lowest CO2 footprint. As water, use water as a scarce resource. And of course, the capital investment that you want to do. So it gives you the measuring capital efficiency by variables such as the IPV or present value or the next solution that I would like to talk about is the CatMax, which is the highly beneficial, where you can change the reactor internals to our proprietary CatMax internals, and they are having the highest mechanical strength. You can put more 6 to 8 more volume percent of catalyst, and that improves your C5 and hydrogen yield, and also there is a weight reduction. I would also like to flash a slide on various retrofit and equipment solutions for the process heat recovery and column optimization. So UOP high flux tubes, like these are the lower temperature approaches and reduce exchanger surface, lower OPEX. Also divided wall column, which is the thermal coupled column for 3 component separation, also including the UOP MD and ECMD trays, which can also give you the lower capex. Compo block exchanger, again, these are the welded plate exchangers, close temperature approach, and lower plot space requirement. Also the weighted surface air cooler, again, the plot area saving, lower capex and OPEX, and lower pressure drops. So here is this is an example how you identify opportunities for CO2 reduction. By drawing a baseline left-hand side, then you draw a step-by-step approach to reduce CO2 emissions through various solutions. From left-hand side, you can see the molecular management, Recovery Max, CatMax, platforming heater optimization, column optimization can give you 40% of CO2 reduction, and the 30% of CO2 reduction can come from CCSU if you implement that one. To help our customer in decision making, we have developed these marginal abatement costs, and these are based on the capital cost, operating cost, and also like whether the solution will be profitable beyond a CO2 limit, or whether the carbon credit incentives are available or not. So if you look at from the left to right, the column width is quite narrow for the for the column optimization because the potential is modest there. So each of the solutions in the left-hand side gives you the x-axis gives you the carbon abatement potential, and the y-axis which gives you the carbon abatement cost. If you look at the second one, which is the recovery max, the width of the bar is quite broad because the potential is quite high. So all the solutions in the left-hand side, they are the solution which removes the carbon per ton of CO2 and also drive economic benefits. Right. Remember what I said, these curves are developed without carbon credit. And if you consider that, even the CCUSU can shift lower to the bottom part of the graph. So emission reduction is a key strategic decision by all stakeholders in the oil and gas industry. Your significant optimization and decarbonization potential exists throughout the naphtha complex. UOP can help with the technology offering pivot towards your problem. This is the last slide for my presentation. Thank you very much for your time and attention.
Thank you, Mr. Gupta, for setting the strategic foundation, and also a big thank you for staying within the time. We now next move from strategy into project execution phase, where decisions directly influence cost, schedule, and long-term operational risk. Our next speaker is Ms. Suhaini. Her presentation will address the challenges and best practices in module installation on floating structures with a focus on design efficiencies and cost optimization. Please give a big welcome to Ms. Suhaini.
Thank you, Mr. Speaker. Okay, before I start, I would like to express my gratitude to the DMT event and then Federation Indian Petroleum Industry for organizing this event. Also, the India Energy Week for giving me the opportunity to present my paper here. Today's topic is about the challenges and the best practice in the module installation on the floater structure, focusing on the design efficiency and cost optimization. Before we go through the presentations, let me go through the agenda. We start with the introduction of the module and followed by the installation methodology, design challenges, design application to mitigate the challenges, technical contribution and conclusions. The module approximately about 36 meter in wide and 28 meter length, which consists of the 5 levels of the main deck that estimated about 4,800 installations weight. It will be installed by lifting with the semi-submersible crane vessel. Unlike the new boat environment of the structure, where we have a tolerance, interfaces, and then the installation conditions can be closely monitored and controlled. The retrofit or the brownfield will introduce the structure geometry uncertainties, the restricted of the deck envelope, and also the complex marine that demand the highly operates for the solutions. To achieve a safe, effective, and also the efficient and cost-effective, that require an integrated approach that combines from the detailed structure design, the fabrication planning, installation engineering, and the risk management. The bumper protection is provided around the structure to assist during the installation phases and to avoid that any snagging that happen. This is some philosophy of the design brief of the module design philosophy, where the design should be covered for the installations, operating, and all the accidental events. The strict environmental come from the wind and also the inertia that due to the hull motion need to consider for the installation and also the operating and the accidental case, where the 5 years will be used for the installations to install the module onto the hull at elevation 62 meters from the mean sea level with the pre-tilt of the 1.5 degree. and the other is like the operating, and also the accidental, where the 200 years return period and 10,000 years return period need to be considered. This approach is using a load resistant factor design approach, and all the critical connection is designed for the fatigue friendly connection. The module is fabricated and also installed. It's fabricated and transported with the interim transportation with the marine transfer vessel. Then it will transfer to the HLV vessel for the hand operation. The module will be secure later on with the sea fastening that designed for the transit conditions. At the field, the HLV will be executed to shelter water lift the module from the MTV. The same primary crane will be used for the offshore installations at site. So for the selections of the MTV vessels, the 330 class has been adopted that suitable compliance with the loadout and also the transportations. Where for the heavy lift vessel is mainly rely on the capacity to lift the module with the hook height at 88 meter height. Okay, this is some the overview, the real executions, where this is the inshore transportation from the yard to HLV, and this is a transfer lift from MTV to HLV, and this is how the module will be secured. For the lifting is executed with the global analysis, where the design is according to the DNV marine warranty and the marine operation and marine warranty. For the lift point is designed with the using the FEA method. For the lifting engineering, we have to consider the pre-tilt conditions for both the pre-tilt and also the pre-heel. This is to minimize the impact and improve alignment during set down later on. So this is the overview of the lifting analysis by Global, and also this is the real execution at site. The lifting point is designed with the LRFD factor of 1.3 is added on top of the lifting action factor. The sling force comes from the global analysis, and the model is refined where the termination point, the lift forces is applied at the FEA model termination point, and also at the pad eye to simulate the module stresses, internal stresses, and connecting the impulse into the lift point FE model. Okay, this is the fabrication aspect for the pad eye. We have like inner pad eye and outer pad eye, where in between we need to slot the solid pin 600 mm. We have to ensure the careful consideration during the fabrication. So the comprehensive method of statement is developed to ensure there is a full bearing contact in between the pinhole and also the solid pin. This is the bumper that will use to guide and assist during the installation, where it consists of the leading bumper. We call it referred as a cow horn that located at the far east to guide the module entry. We also have the lateral bumper located at the south and or the west north of the platform to ensure the final alignment achieved on the north-south direction. And lastly, we have like this long stopper bumper that can provide the control for the east-west movement. This is the design of the bumper, where we have like it's calculated like from the 4,800 metric ton installation NTE weight. The impact of the bumper that considered is normal to the bumper structure, the frictional vertical, also the frictional horizontal, and it applies simultaneously at the impact location. The impact location apply at the mid-span and also the bumper ends to cover the every scenario of the installation. The additional LRFD factor of 1.3 has been considered. So the local damage and plastic deformation of the bumper is acceptable if the bumper functional aspect remain effective for the post-deformation. Okay, this is the FEA, the von Mises plot for the impact at the mid-span, and then the lower figure is impact at the bumper ends, and also the strain plot from the long stopper. For set-down and dampening system, the set-down dampener are installed within the module to module legs to absorb the impact forces and reduce the dynamic loadings on the hull. The steel receptor and the elastomer bearing assembly located at the tubular at the main tubular at the support point, 4 support point. Module also designed and verified to withstand all the external forces encountered from the set-down operation for initial lifting until the final positioning. The design structure to ensure the set-down are effectively transferred to the hull while accommodating the variation in the hull trim and heel during the transfer. So for this case, we have the X set-down scenario that has been considered for the set-down process. This case is represent the critical condition for the load transfer and the integrity during the installations. That's set-down scenario is simulated to maximize the impact forces and for design conservatively to cover the uncertainties during the installation. The other check that we carry out is like to check the point contact where to assessing the plastic deformation due to the module landing with the inclinations. For this case, we have considered 4.3 degree inclinations, and from the FEA result, the plastic deformation is assessed and it can be negligible as it is not impact the welding condition and then the deck leg integrity. We come up with the design challenges for the set down at the existing semi-submersible module. We have to reduce the dampening system is designed to reduce the contact stiffness, where thereby minimize the impact of the loads and also the module installations. We have considered the minimum, mean, and or maximum of the installation weight we adapted from the weight control report. The capacity of the dampening system is limiting to the existing location of the hull, and then although the hull is exhibit with the 6 degree of freedom stiffness, but only vertical stiffness can be considered during set down and also the pre-weld phases. The dampener have to restricted and tuned to the vertical stiffness of 80% on the static load with the 0.2 absorptions only. So, and due to the sensitivity for the dampener on the module and COG, the final rubber stack and also the stroke is adjusted for the model bearing and fabrication phases. Set down contact. This is the design of the set down contact. Where this is the critical interface in between the module and the hull at 4 locations. As per design, it's a full contact and without no gap. And then the pre-survey is conducted on the base plate, and the result determine the cut-off length of the green module leg. During the design, actual installation condition, the intermittent contact is found that resulting the high stresses, concentration stresses on the circumference of the leg. The load mainly is transferred to through the weld, and due to the gap, we need to assess back the strength and also the fatigue check for the post-installation condition based on the survey. To mitigate that, we come up with the bevel preparations plan. Where we have gap, we introduce the full penetration weld. To achieve this, the additional guiding is provided with the minimum age preparation of the 10 mm. And the well is filled with the buttering, and also the joint is prepared with the more bevel angle to facilitate the complete penetrations. So the design is still maintaining the concave profile to minimize the concentration effect at the well too. So for the
I
fatigue,
request Ms. Suhaini to please hurry up. I would request you to please wind up fast. We're already short of time.
Okay. Give me 1 minute. Okay, I just make it quick. This is the strength check. We need to come up with the strength check and the fatigue check for the non-contact. Okay, this is the profile. At the top is a profile for the check for the strength check, where we model the 3 mm gap with the full welding penetration profile. And below is the result that come out from the strength check. This is the SCF. Other than this, we need to check for the fatigue. So the fatigue mitigation strategies include the SCF and the grinding method. This is how we derive the SCF with the FEA for axial. And this is in plane bending, and this is for the out of plane bending. So for the fatigue assessment, is performed with the SNN curve from the NVGL RP203, where the root is assessed with W2 curve, and the toe is assessed with the D curve. The connection is considered critical and non-inspectable, therefore the certificate 10 is considered, where the requirement become like 3055. The implementation of the welding and toe grinding in the SCF well, we improve the fatigue performance. As you can see here, the fatigue life is like achieved at 1100. Okay, this is my last slide for the technical contribution and the conclusions. A comprehensive engineering methodology should be carried out for the integrating the large module to the semi-submersible hull. The work scope should be cover the full cycle of the installation engineering, starting from the loadout, inshore transportation, sheltered water transfer, offshore installations using the semi-submersible heavy lift vessel. The installation strategy address the lifting configurations, crane operating limits, rigging arrangement, hull ballasting and pre-take requirement necessarily to execute the operation with highly constrained at the highly constrained deck environment. So overall, the installation engineering, detailed structural modeling, the bumper and dampening system design, the fatigue qualification provide a full compliance of the solution requirement that ensuring the safe installation, the long structural integrity for the module and hull transfer. Thank you.
Thank you, Ms. Suhaini. Now, from large-scale project execution, we will shift our focus to equipment-level innovations, one of the most effective levers for improving energy efficiency in a process plant. For this, I would request Mr. Indrakumar Gore and to please come on the stage and give his presentation. And his presentation will evaluate the corrugated tube heat exchangers for industrial applications and based on an experimental approach. Please give him a big hand.
Good afternoon, everyone. So today I'm going to present the experimental analysis of corrugated tube double pipe heat exchanger. So when we talk about heat exchanger, the first thing comes in mind is a shell and tube heat exchanger because of its robust construction. It can be used for high temperature and pressure application. However, when we talk about shell and tube heat exchanger, it has very low effectiveness, and hence we require very large heat transfer area for given duty. The second best choice, we have a plate type heat exchangers which has very high effectiveness, which requires very lower heat transfer area and it's compact in size. However, the problem with plate type heat exchanger is the operating pressure and temperatures. It cannot withstand high pressures and temperatures, so we need a solution, a heat exchangers which can withstand high pressure, high temperature at the same time, which is as effective as a plate type heat exchangers. So to enhance the heat transfer, we have some methods like some of them are active methods, some of them are passive methods. Passive methods are those where we change the heat transfer geometry, like a corrugated tube or twisted tube that improves the heat transfer coefficient. Sometimes we go with the active methods where pulses like flow pulsations are created to disrupt the boundary layer and improve heat transfer coefficient. If you see in the picture, there's a conventional shell and tube heat exchangers. There is and the corrugated tube heat exchangers. There is no actual difference between shell and tube and corrugated tube heat exchangers. The only tubes is different. In a corrugated tube, we have a corrugated tube in place of plain tubes. These corrugated tubes are a tube with spiral indentation on which the corrugated tube with design parameters for corrugated tube. The design parameters includes the depth of corrugation, angle, and the pitch of corrugation, which can be controlled as per the application.
Corrugated tube heat exchanger, which is different from the conventional ones. A corrugated tube is produced by indenting a plain tube in helical pattern without any thinning of wall thickness or development of stresses in the tube. The helical indentation imparts two flow regimes to the fluid in the corrugated tube, spiral at the core and eddies at the periphery. Thus, corrugated tubes induce turbulence in the fluid even at lower velocity at the peripheral layer, which results in higher heat transfer coefficient. The two-regime flow enables thorough mixing of the fluid, ensuring homogeneous fluid mass rather than layered flow pattern. The corrugations provide a channel to the condensate layer formed on the surface of the tube, always providing a fresh new surface to the vapors to condense. The condensation is thus drop-wise and not film-wise as in the case of plain tubes. This reduces the heat transfer area by half. Higher peripheral turbulence due to corrugations does not allow the suspended solids in the fluid to settle on the tubes, thus giving it a self-cleaning effect which results in reduced fouling. This ensures longer running time without stopping for cleaning. The response to CIP cleaning or mechanical cleaning by brush is better in comparison to a plain tube heat exchanger due to the discontinuous layer of deposition. Corrugated tubes also offer homogeneous temperature distribution in the tube. The corrugated tube heat exchangers are compact, economical in cost, efficient and versatile with reduced fouling.
Okay, so what we are trying to do here is, we have combined advantage of plate heat exchangers and a shell and tube heat exchangers in a corrugated tube heat exchangers. Now, this corrugated tube technology, actually these corrugated tubes are manufactured in our Amarnath, Mumbai factory. In the manufacturing process, there is no material removed from the surface. There is no additional stresses are created, ensuring integrity of the tubes. So these tubes can be manufactured with all materials like titanium, hastelloy, monal, inconel. Regarding the research or development of these corrugated tubes, we already have done research on single phase and two phase applications. We have established an experimental facility to measure the heat transfer and pressure drop characteristics for such tubes. The background of this study, the corrugated tube technology is not new; it is already in the market. A lot of scholars have already studied this. Also, Kinam Engineering Industries are manufacturing these heat exchangers since 1.5 decades. Even with the existing research, experimental data is necessary to validate the performance in real life. In the current experiment, we have determined experimentally heat transfer characteristics and pressure drop characteristics for corrugated tube for the fluid flowing through the tubes. We have tested 3 different geometries like KIC 1, 2 and 3. Only we have changed the depth of corrugations. The KIC 1 has depth of around 0.5 mm and the depth goes to up to 0.9 mm. This is just a setup where the liquid flows through the tubes, and in the annular section between the 2 tubes our steam is fed. Okay, this I'll just go to the next slide. This is the complete PNID of the test rig, where we are actually testing both plain tube and corrugated tube simultaneously to get the accurate results. This is a steam generation section. Steam is generated in a steam generator using hot oil. We ensure that steam is generated at little bit of 3 to 5 degrees Celsius superheat, so that when it enters to the section, it will be at saturated condition. There is a water circuit. In the water circuit, the flow rate of water is controlled by using control valves to the required Reynolds number value. The tube which we have tested is having around 2-meter tube length, and the water temperature is maintained at around 30 to 35 degrees Celsius. This is the test rig. So we have measured the data. In the data measurement, we have measured the pressure drop using differential pressure transmitter with the least count of 1 Pascal. The temperature measurement is done using thermocouple with accuracy of plus or minus 0.1 degree Celsius. The water flow is adjusted to achieve desired Reynolds number value. And the temperature readings are taken every 10 minutes after thermal equilibrium is reached, and the final readings is recorded before adjusting to the next value. To validate the performance, to validate the data recorded, we have done repetitive testing, and the maximum uncertainties for the measurement of Nusselt number and Reynolds number is in the range of 3.6 to 4.2%. The data, we have used simple energy balance equations. The energy lost by hot fluid is taken by the cold fluid. The overall heat transfer coefficient is UA delta Tm. Since we are using steam in the shell, steam is having very high heat transfer coefficient as compared to the water, and the heat transfer is almost controlled by the water side only. So here in the whatever heat transfer coefficient we are measuring, that coefficient is approximately equals to the coefficient of cold side inside the tubes. Again, to validate the test rig, we have conducted experiments with the straight tube for a Reynolds number of 500 to 100,000, and we have found maximum deviation of 4.1%, which is in acceptable limit. So which shows that the experimental setup is accurate and reliable for the measurement of pressure and Nusselt number. This is the heat transfer data. It is like friction factor data and heat transfer data. We can see that there is a spike in the heat transfer Nusselt number value at around 2100. So it shows that the critical Reynolds number for the system is around 2100. As I told you, we have tested 3 different tubes. So here the chart shows the friction factor data and heat transfer data for 3 different tubes having different depth. So in the first chart, you can see we have plotted the ratio of friction factor of corrugated tube to the plain tube against Reynolds number, and we have seen that highest ratio is around 2.5 for 0.9 mm depth of the corrugations. At the same time, if you look at the heat transfer data, the ratio of Nusselt number is highest for KIC, for high depth of corrugation of 0.9, And we have found that the Nusselt number value increases in a laminar region up to turbulent region, and then it slightly reduces. To specify the performance evaluation criteria for this, for the corrugated tube, we have plotted PEC against the Reynolds number, which shows that the amount of increase in heat transfer coefficient with respect to the rise in the pressure drop. The ratio should be more than 1. And we have found that for all 3 tubes up to 100,000 Reynolds number, the PEC value is more than 1. So we recommend this corrugated tube heat exchangers for almost all values of Reynolds number. The conclusion of the study is that we have found that the excellent performance of excellent heat transfer performance of corrugated tube for laminar and turbulent region. As we keep on increasing the depth of corrugation, the pressure drop and heat transfer coefficient increases. The undergoing and future study, we are actually testing different corrugated tube profile with viscous fluids. In the future, we are also going to test a different temperature, different corrugated profile for fluid condensation outside the tubes and fluid condensation inside the tubes. The motivation for the study is to evaluate different corrugated profile and find the most effective corrugated profile for particular application. Our aim is to reduce the cost of heat exchangers and improve heat transfer coefficient and make heat exchangers as compact as possible. So, thank you.
Thank you, Mr. Indra Kumar, for a wonderful presentation. We now move into live operations, where real-time decision making and digital optimizations directly translates into profitability, especially in complex and high severity units. For this, I would call upon Ms. Rijumoni Boro, and her presentation will focus on enhancing the delayed coker profitability through online process optimization. Please give her a big hand.
Thank you, sir. A very good afternoon to everyone. So today I am going to present a case study on improving the operability of a delayed coker unit through process optimization. So this is the disclaimer slide. So in today's presentation, I am going to discuss a case study outlining the key issues that arose during delayed coker operation at one of the Indian refinery and the approaches that were made to resolve the same. So this is a general introduction of a delayed coker unit. So delayed coker unit is a secondary processing unit used for upgradation of bottom of the barrel heavier petroleum residues into lighter components like kero, naphtha, diesel, etc. And it also produces coke as a byproduct. So depending on the type of feedstock and operating conditions, anode grade coke or fuel grade coke are produced. The general goal of a delayed coking process is to maximize liquid product yield while minimizing the coke production. So coming to the case study, these were some of the issues. Okay, so actually this is moving fast. So coming to the case study, so these were some of the key issues that were faced during refining operation. So the first was that the unit was unable to increase its fresh feed as per design due to limitation in its gas con section and lower coke drum margin. And the second is the coke fines carryover issue was observed from the coke drum despite of dosing of anti-foaming agent. And the third is continuous flaring from the unit was observed due to high gas generation. And also the unit had a quench column which purpose is to quench the overhead coke drum vapors before it entered the main fractionator column. And it also generated residual fuel oil as a byproduct which is further used as a fuel oil in the furnaces. However, due to its low demand, its generation had to be minimized. So in this slide, we will see what were the strategies that were employed to resolve the issues mentioned in the previous slide. So the first is the unit was unable to increase its fresh feed. So the unit was already operating at a high recycle ratio of around 60 to 65%. So recycle ratio is nothing but the difference in secondary feed and primary feed upon the primary feed. So the recycle stream enters the main fractional column bottom along with the fresh feed, and it is measured at a heater inlet. So reduction in recycle along with gradually decrease in the column bottom temperature helped in drawing more fresh feed to the column, and thus the total fresh feed to the unit could be increased. And the second is coke fines carryover issue was observed from the coke drum, which could be attributed to higher coke yield. So higher recycle ratio led to higher coke formation, as the recycle stream consists of the heavier fractions which undergoes additional thermal cracking when fed back to the coker, and this contributes to the overall coke production. So this higher coke yield led to faster filling of the coke drum, surpassing the safe filling margin, and overfilling of the coke drum led to coke fines carryover issue along with the vapors leaving the coke drum. So this was prevented by lowering the coke drum cycle from 24 hours to 20 hours, and subsequent reduction in recycle helped in reducing the overall coke yield and thus prevented the issue. And also high recycle ratio led to higher gas generation, and reduction in recycle ratio helped in reduction of gas mix and thus prevented flaring from the unit. So as mentioned, the unit also had a quench column which generated residual fuel oil as a product. However, due to its low demand, its generation had to be minimized, so it was reprocessed back to the coker, and thus the overall black oil make from the unit could be reduced. So now we will see how recycle reduction was done in the case without RFO recycling, that is where RFO was withdrawn as a product from the quench column. So recycle reduction in this case was done by gradually decreasing the secondary feed in small steps while keeping the primary feed constant. Also the column bottom temperature was reduced gradually. So with this exercise, about 28% reduction in recycle work could be achieved. So these are the initial and final conditions as we can see. So as a result, reduction in coke make by about 28% could be observed, with corresponding increase in distillate yield. Also low heater feed to the furnace led to lower heater load, and the reduction in FG firing was reduced by around 80 kg per hour, and also the reduction furnace skin was observed by around 3 to 5 degrees Celsius, and the reduction in drum pressure was observed by around 0.1 bar. Also the liquid and product coke properties were well within the acceptable limits. So this is the case where RFO was recycled. That is, the RFO drawn from the quench column was processed back to the main fractioner column. So in this case also, recycle reduction was done by gradually reducing the secondary feed in small steps while also reducing the column bottom temperature. So to maintain the bottom temperature, fresh feed inflow to the column increased as the temperature was lowered. So with this exercise also, 28% reduction in recycle was achieved. And so as a result, the reduction in coke make was around 1.58%. So RFO could be completely eliminated from the system, and the primary feed increased by around 10%. And the liquid product and properties are well within the acceptable limits. And also a gross profit of around 10 to 12 crore per year was achieved due to overall increase in the distillate yield. So to summarize, higher recycle ratio can increase coke yield, reduce distillate yield, while also can increase the heater duty. Conversely, operating at a lower recycle can help improve fresh feed throughput. It can reduce the coke yield, and it can lower the heater duty, and it can also extend the furnace run length over the long term. However, optimization of a reduction in recycle ratio can only be done up to a certain limit, beyond which low heater velocity through the passes can increase the risk of coking. So to conclude, optimization in recycle ratio can improve the overall profitability of a delayed coker unit. So with this, I would like to conclude my PPT. Thank you so much.
Thank you, Ms. Boro. And with this, I thank all my speakers for their insightful presentations. As you must have all noticed that today's session clearly demonstrated that optimizing efficiency and managing risks are not a single initiative or an isolated function. It's a continuous process which has to be taken from strategy, from project execution, equipment design, and then from real-time operations. I hope that the perspectives shared today would provide with the insight that can be applied across refinery and petrochemical complexes, and we can make them much more safe, more efficient, and more sustainable operations. With this, we come to an end for this session. For the paucity of time, it will be difficult for me to take Q&A sessions. I would request all of you and encourage you to please interact with the speakers after the session and on the cup of a coffee, and then we can resolve all your queries, whatever you have. So thank you once again to all of you, and I wish you all a very happy, fruitful IEW coming days. Thank you.